In the middle of our Milky Way galaxy is an amazing group of stars called Westerlund 1. It's a huge and active hub of cosmic activity, filled with some of the biggest and brightest stars in our galaxy. Recently, the James Webb Space Telescope used its cutting-edge technology to take a closer look at Westerlund 1. These new discoveries reveal incredible details about the cluster, its stars, and the forces that shape how they grow and change. In this video, we'll uncover the details of Westerlund 1 and explore why this stellar cluster is key to unraveling the mysteries of our universe. Westerlund 1 is a remarkable star cluster located about 13,800 light-years away in the constellation Ara. It was discovered in 1961 by Swedish astronomer Bengt Westerlund and quickly gained attention for its immense size and unique stellar population. This cluster stands out for its extraordinary mass, estimated to be between 50,000 and 100,000 times that of the Sun, making it one of the largest and most luminous clusters in the Milky Way. It is classified as a superstar cluster, a home to some of the galaxy's most massive and energetic stars. These include red supergiants, yellow hypergiants, and Wolf-Rayet stars, stellar types known for their immense size, brightness, and short lifespans. The cluster's estimated age of 5 to 10 million years places it in a dynamic phase of stellar evolution, as many of its stars are undergoing rapid changes or nearing the end of their lives. One of its standout features is Westerlund 1-26, a red supergiant so enormous that its outer layers would extend beyond Jupiter's orbit if placed in our solar system. Stars like this are rare, and their presence in this cluster makes it a laboratory for studying these cosmic giants. The cluster's extreme density is another remarkable trait. In a space spanning just 3.26 light-years, tens of thousands of stars are packed together. This close proximity leads to intense gravitational interactions, influencing the star's motions and how they evolve over time. This cluster also plays a vital role in the broader processes of star and planet formation. Massive clusters like this are thought to be the birthplaces of most stars in the universe. As their most massive members end their lives in supernova explosions, they scatter heavy elements, like carbon, oxygen, and iron, into the surrounding space. These elements are essential building blocks for planets and, ultimately, life. Finally, the cluster provides a bridge between the Milky Way's present state and its ancient past. By studying its dynamics, structure, and stellar composition, astronomers gain insights into how the galaxy evolved over billions of years. Using its advanced infrared capabilities, including the near-infrared camera, NIRCam, and the mid-infrared instrument, MIRI, Webb was able to penetrate the obscuring dust and reveal the intricate structure of the cluster and its surroundings. It discovered a diffuse nebulosity surrounding the cluster's core. This nebulosity is made up of droplet-like structures that seem to interact with the massive stars in the cluster. These features are likely sculpted by intense radiation and powerful stellar winds emitted by the cluster's stars. Such interactions provide critical insights into how massive stars shape their environments, influencing the distribution and movement of gas and dust. Another striking finding was an elongated, trunk-like structure stretching about 3.3 light-years toward the cluster's center. This filament appears to be a channel of gas and dust being drawn into the cluster by its strong gravitational pull. This process could lead to the formation of new stars, showcasing the dynamic and ongoing star formation occurring within Westerlund 1. The discovery of this trunk helps astronomers better understand how material flows into massive clusters, fueling their growth. Webb's observations also revealed extended shells around several M-type supergiant stars in the cluster. These shells vary in shape, with some elongated structures pointing away from the cluster center and others showing narrow outflows in specific directions. These features are thought to result from mass loss during the late stages of the star's lives, driven by strong stellar winds. Observing these shells provides important data on how massive stars lose material before they explode as supernovae. One key discovery by Webb is the role of feedback mechanisms in massive star clusters. These stars emit intense radiation and stellar winds that shape their surroundings in two ways: by compressing nearby gas to trigger new star formation, or by dispersing gas, which stops star formation. This dual role of creating and destroying star-forming conditions is central to modern astrophysics. The elongated trunk-like structure in Westerlund, one shows how gravity channels material into clusters, fueling star formation. This finding helps refine models of how stars form, especially in dense regions of gas and dust. Westerlund 1 also serves as a nearby example of similar starburst regions in distant galaxies, which are harder to study in detail. The cluster reveals critical details about the life cycles of massive stars, including rare types like red supergiants and Wolf-Rayet stars. These stars enrich the galaxy with heavy elements such as carbon, oxygen, and iron, which are released as they lose mass and eventually explode as supernovae. Understanding these processes provides valuable insights into how essential elements for planets and life are distributed throughout the galaxy. It also offers a unique perspective on the dynamics of densely packed star clusters, where intense gravitational interactions shape the motion and fate of individual stars. These observations help astronomers better understand how massive clusters evolve and influence the structure of galaxies. Thank you for watching. If you enjoyed this deep dive into Westerlund 1 and the incredible discoveries of the James Webb Space Telescope, don't forget to like, subscribe, and share. Stay tuned for more exciting journeys into the cosmos.